Okay, so the problem we are doing is question number 6. What is the magnitude and direction of the electric force that the plus 5 nanocoulomb charge experiences due to the other 3 charges? So to find the electric force, we're going to find the net electric field on the plus 5 nanocoulomb charge right here. So we are considering this our test charge, and we want to find the net electric field from these 3 charges: point A, which is plus 2 nanocoulombs, point B, which is 0.7 nanocoulombs, point C, which is negative 3 nanocoulombs. And to start this problem off, we want to find the direction of the electric field due to these charges. So to do that, we're considering our test charge as the origin and set up our x and y axes according to that. So the direction of the electric field of this charge points away from it because it is a positive charge. So the direction would be going to the right. And because this is a negative charge, the electric field that it exerts on the test charge is facing towards it because it's a negative charge right here. So overall, we just want to find the x and y components and then add them together. So point A is already in the x direction. It has no y component. And then we just plug it into the equation. E equals Coulomb's constant times the charge divided by the distance squared. And the distance point A is 6 centimeters away from the test charge, and point C is 4 centimeters away from the test charge. So Coulomb's constant is 8.99 times 10 to the 9th. So we plug that into the equation, but before we can plug in the charge of point A, we have to convert it to coulombs. So to do that, we just multiply it by 10 to the negative 9. So we'll put that in the numerator, and then for the distance r, we convert centimeters to meters. So we divided the 6 centimeter distance right here by 100. So that turns out to be 0.06 meters squared. And so we plug that into our calculator, and the answer we get is 4,994.44 newtons over coulombs. And so to find the magnitude of the electric field of point C, we plug it into the same equation. We make the same conversions. So to convert nanocoulombs to coulombs, we would multiply it 3 times 10 to the negative 9, which gives us coulombs. And then to convert from centimeters to meters, divide the distance 4 by 100, and we get 0.04. We plug that into the equation and make sure that's squared. And once we plug it into the calculator, we get 16,856.25 newtons per coulombs.
So to find the electric field on our test point, due to point B, which has a positive 7 nanocoulomb charge, is a little more complicated because it doesn't intersect the point at a right angle already. So we're going to have to first of all find the net electric field due to point B, and then break that electric field up into its components. So to find the net electric field, we do the same equation that we used before, except for this time we have to solve for our r using the Pythagorean theorem. So we have this value of r based on that math. So we have 4 centimeters squared plus 6 centimeters squared, the square root of that number, that whole quantity squared. So the net electric field due to point B comes out to be 12,101.923 newtons per coulomb. And then to break that electric field up into its components, we assigned this angle here to theta, and then solve for the value of theta, again using trig. So the tan inverse of 4 centimeters over 6 centimeters gave us the value of 33.69 degrees. To find the x component of our field, Because the x component was this side here, and this angle here is theta, we used the cosine. So we took the total electric field multiplied by cosine of theta to find the x component equal to 10,069.42 newtons per coulomb. Very similar to how we found the x component, we find the y component by multiplying the total electric field due to point B and multiplied by the sine of theta. And after doing that calculation, we came to find the y component due to point B is 6,712.93 newtons per coulomb.
Okay, so to finish off this problem, we need to find the total electric field acting on this particle here. So we can do that by breaking it down into x and y components. So we find the sum of the electric field acting on the particle from B plus the x direction of the electric field from A. We add those up together to get the 15,063.85 newton per coulomb. And we do the same thing in the y direction. So we find the y direction from this particle acting on this particle here, minus the electric field acting from this particle. Now it's important to note that this is a negative here because this is a negative charge and this is a positive charge, so that attraction is going to create that negative y direction pull. And so you see that negative here, and that is why we get a negative 10,143.31 newtons per coulomb. And so from there, we want to find the total electric field acting on this particle. We do that by using Pythagorean's theorem here, just plugging in these equations here, and we get the total electric field to be 18,160.57 newtons per coulomb. So now that we have the total electric field, we can find the force acting on this particle by using this equation. Force equals the total electric field multiplied by the charge of the particle here. And so we just plug in this number, and this is the charge of the particle to begin with. Just do a simple conversion to coulombs, and we get 9.08 times 10 to the negative fifth newtons over here. So that's the total force acting on the particle. The final part of this problem is to find the angle at which the force is being acted on. We do that by taking the tan inverse of the opposite over adjacent here. We plug these numbers in here, and we get 34 degrees for this angle, and that it's 34 degrees below the x-axis. That's a final answer.
Alrighty.